Hello everyone, welcome to our channel Mathematics Parshala. This is a problem of GATE 2024 Mathematics Code MA. This is a question from Topology and Functional Analysis. So first we read the question. Let L to Z be the set of all such sequences, this type of, such that xj belongs to R and summation j equal to 1 to j equal to minus infinity to infinity xj square less than infinity, endowed with the inner product xy equal to this. So such elements are like this. Say here x minus 2, x minus 1, x0, x1, x2 dot dot. So if we take x and y from this L to Z, say y minus 2, y minus 1, y0, y1, y2 dot dot, then this inner product is defined in this way, that this is dot dot up to this x minus 2 into y minus 2 plus x minus 1 y minus 1 plus x0 y0 plus x1 y1 plus x2 y2 plus dot dot, in this way. Now here t is defined on this L to Z by this t xj, j belongs to Z, equal to, if it is yj, j belongs to Z, then this yj is equal to xj plus x minus j by 2. So actually, if we consider the space simply L2, the sequence space, such that summation mod xn square less than infinity, so simply the elements will be, then the elements are, say if we take one element x belongs to L2, then x is a sequence, that means x is a function from n to R, satisfying that summation xi square less than infinity. So here this type of functions are from Z to R. So simply here this n is replaced by this set of all integers Z. So this type of elements are in this set L to Z. So actually if we write this L2 by simply L to n, we can write. So simply here this L to n is like L to Z. Okay. So the set is clear now. Now T is defined in this way, then which of the following is or are correct options? So one by one we will study the options. See first, if we take arbitrary x belongs to L2, then this Tx equal to this Txj j belongs to Z, and this is defined by in this way, that yj, and yj is actually our xj plus this xj plus x minus j by 2, j belongs to Z. So simply we can write this as half xj, j belongs to Z, plus half x minus j, j belongs to Z. So clearly this is actually the identity operator. So this is I at this xj j belongs to z, and we are writing this operator by j, that is j x j, j belongs to z, where this j is defined by, where this j is defined by this j x j, j belongs to z is simply just minus of this element. So this is actually uh, x minus j, not actually minus, so the suffixes will be just changed in this way, x minus j, j belongs to j. So this way j is defined. So now t is actually here I half this ix plus this jx. So this is actually half I plus j at x, and this holds for all x belongs to this L to Z. We have taken arbitrary element x belongs to this L to Z. So we have this t equal to half I plus j. Okay. So now see, simply just if we take arbitrary x, then our what is our norm tx, calculate we calculate this norm tx. So norm tx equal to half this I plus j at x, norm of this element. So this is norm half x plus jx, norm of this element. So using triangle inequality, we have half norm x plus half norm jx, and also clearly this norm jx will be actually equal to this norm x. So this is half norm x plus half norm x. By the definition of j, simply if we consider norm jx, then that will be also summation j equal to minus infinity to infinity mod xj square, and that is actually our norm x. So this is equal to actually norm x. So what we get from here, that norm t is less than t is bounded and norm t is less than equal to 1. And also simply if we take, simply if we take one fixed element, that x equal to, say z equal to, simply taking just all such members are 0 0, only this x0 is 1 and the other elements are also 0. So clearly this element will belong to the unit ball of this space L to Z. Actually this will be in norm 1, so this will be unit sphere, this will lie on the unit sphere of this space, that is S L to Z. We can denote this by S L to Z. So clearly this, for this element z, our what is our norm tz, we can check. So this norm, this will be simply by definition of t, this will be simply just the same, sorry, this will be simply 0 dot dot 0 0 1 0 0 dot dot norm of this element, and this will be simply 1. So from this norm tx less than equal to 1 for all x belongs to L to Z, and at one element z, norm tz equal to 1, this implies that norm t equal to 1. So the operator norm is equal to 1. So here the option B is the correct option. Now come to the option C. So for this, see, simply we will just see here first that this this j, we define j in this way. So here this j will be our self adjoint operator, that is j star will be equal to j. We first prove this. So simply calculate, take arbitrary element xy belongs to L to Z, and we will calculate what is our inner product jxy and what is our inner product xjy. So this is simply will be summation, just we have taken x equal to xj and y equal to yj, then this will be summation j equal to minus infinity to infinity, as jx will be x minus j, so this will be x minus j yj, and this will be summation j equal to minus infinity to infinity xj y minus j. And simply if we just substitute some this j equal to minus k or something, simply we will get these two elements will be equal. So we have from this inner product jx, or simply if we write these two expression explicitly, simply we can see that these are equal. So this inner product jx y equal to inner product x jy, and that must imply that j is self adjoint, that is j star equal to j. Now simply calculate what is our t star. So t star will be equal to half I plus j whole star, and this will be equal to half I star plus j star, and we all know that identity operator I is self adjoint, so this will be I star equal to I, and we have proved that j star equal to j, so this is equal to this, that is equal to t. So what we get, t is self adjoint. So come to the options. Option C says that t is self adjoint, so option C is the correct option. Now come to this option D, range T is closed. So for this, this is for option C, and this is for option D. So now simply let me write what is our range T. This range T is equal to all such Tx such that x belongs to L to Z. So this is actually, see, for an arbitrary x equal to xj, j belongs to z, how is loop tx? So tx is actually our looks like this dot dot, this element is our x minus 2 plus x2 by 2 comma x minus 1 plus x1 by 2 comma x0 plus x0 by 2, that is 2x0 by 2, that is x0, comma x1 plus x minus 1 by 2 comma x2 plus x minus 2 by 2, and so on dot dot. So clearly this term and this term is equal, this term and the latter term of this is equal. So clearly simply we can write that tx is looks like this xj, j belongs to z, such that this all such xj belongs to R, with our xj equal to x minus j, xj equal to x minus j, j belongs to j belongs to n union singleton 0, with this summation xj square is less than infinity. J equal to minus infinity to infinity, and as these terms are same, so simply this we can write more simply that xj, j belongs to z, such that this xj belongs to r, comma xj equal to x minus j, such that j belongs to natural number set union singleton 0, such that summation xj square j equal to simply 0 to infinity is less than infinity. So simply we can write this one element of RT like this, that all such elements as this will be same. So simply we can write this as x0, x1, x2 dot dot so on. So just extra one term from the elements of L2. So simply this is actually we can define an isomorphism from this RT to L2. So this is actually isomorphic to this L2 space. So here n actually we can write or n union singleton 0, n union singleton 0, and this will be also isomorphic to simply L2 space, and which is clearly closed. So now look at option D, that range T is closed. So here option D is the correct option. Now look at option A, that T is a compact operator. Let us recall the definition of compact operator. An operator T is said to be compact if T maps every bounded set to the relatively compact set. That means, so for A is bounded implies TA is relatively compact. Relatively compact, that means closure of TA is compact, TA bar is compact. So if we can show that for any bounded set A in this L to Z, TA closure is compact in L to Z, then it will be proved that T is compact. But here actually we will show that T is not compact. So we have to find one example of a bounded set such that T of that bounded set will not be relatively compact. So simply we will take the closed unit ball of this space and write this as B. So that will be B L to Z, that is all such x belongs to L to Z, such that norm x less than equal to 1, and if we take an arbitrary element x belongs to B, then clearly this norm Tx will be actually this element, norm of this element. So this element is like this: x2 plus x minus 2 by 2, comma x1 plus x minus 1 by 2, comma x0, comma x1 plus x minus 1 by 2 dot dot norm of this element, and simply this will be summation j equal to minus infinity to infinity this xj plus x minus j by 2 whole square. So by simply calculating this, we will get summation j equal to minus infinity to infinity xj square plus x minus j square plus 2 xj into x minus j by 2. Then this will be this will be in 4 in the denominator. So this will be actually summation 1 by 4 taking common. We will get summation j equal to minus infinity to infinity xj square plus summation j equal to minus infinity to infinity x minus j square plus summation 2 of this xj into x minus j and j equal to in summation minus infinity to infinity. Now simply an inequality, from an simple inequality we get that this xj square plus x minus j square is greater than equal to 2 xj x minus j. So using this inequality we get this less than equal to 1 by 4 summation this j equal to minus infinity to infinity xj square plus summation j equal to minus infinity to infinity x minus j square plus summation j equal to minus infinity to infinity this xj square plus x minus j square. So simply calculating this we will get half summation xj square j equal to minus infinity to infinity plus summation j equal to minus infinity to infinity x minus j square, and clearly this summation xj square is actually our norm x, and also summation minus x minus j square is also our norm x. So this is equal to actually norm x. So what we get actually here, and norm x is 1, so we get that norm tx less than equal to 1 for all x belongs to this b. So that means this tb is definitely a subset of b, and also as this uh, range space of t rt is equal to simply L2. So simple just verification, on simple verification we can get that this TB is actually the closed unit ball of this L2 space. So now we know that L2 is not finite dimensional, and hence this BL2 is not compact. Is not compact, and uh, also as this BL2 will be closed, so this TB closure equal to this BL2 closure equal to this BL2 is not compact, but this B is bounded. So now we have an example of a bounded set in L2Z such that TB is not relatively compact as TB closure is not compact. So T is not a compact operator. So now look at option A. See here, so T is a compact operator. This is not the correct option. So here option A is not the correct option, and option B, C, D are the correct options. This is the solution of this problem. Thanks for watching.